Hello everyone, in this video we will be talking about emissivity and a law which is known as Kirchhoff law. So already we have discussed about the emissivity epsilon. We know that out of all bodies at the same temperature, the black body will be emitting maximum amount of energy, and the energy emitted by any other body at same temperature will be lesser than that of black body. So you can define a ratio which is known as emissive power of real body to emissive power of black body, which is known as emissivity. This emissivity will be varying from 0 to 1, and this emissivity is equal to 1 for a black body, and we know that this can be written as E by EB. From the previous Stefan Boltzmann law, the total emissive power of a black body can be written as it is proportional to fourth power of absolute temperature. This is equated to sigma T raised to 4, where sigma is known as Stefan Boltzmann constant. So you can write epsilon equal to emissivity equal to E divided by sigma T raised to 4. Therefore, for any real body, you can write the emissive power as epsilon into sigma T raised to 4. This sigma T raised to 4 is the emissive power of black body, and as epsilon is varying from 0 to 1, it can be 0.8. Then for a real body, it will be 0.8 times sigma T raised to 4 only. And here you can define this emissivity property for a particular wavelength also, which will be known as spectral emissivity or monochromatic emissivity, which is denoted by epsilon lambda, which is equal to emissive power of a real body for a particular wavelength to emissive power of a black body for that same particular wavelength. So you can write E lambda equal to epsilon lambda into black body, EB lambda, monochromatic emissive power of black body. So from this you can find this total emissive power for that real body. This is actually real body by integrating over the entire range 0 to infinity epsilon lambda EB lambda into D lambda. And you can find the total emissivity if you are having this monochromatic emissivity. So total emissivity is total emissive power of a real body to total emissive power of a black body, and this total emissive power of a real body is this one, 0 to infinity monochromatic emissivity epsilon lambda into EB lambda into D lambda, and total emissive power of black body is 0 to infinity monochromatic emissive power into D lambda, that is integral 0 to infinity EB lambda D lambda. So in this way you can obtain this total emissivity epsilon if you are having monochromatic or spectral emissivity epsilon lambda. So this is the things about emissivity and spectral emissivity. Next we will be seeing a law which is known as Kirchhoff law, which is relating the emissivity and absorptivity of radiating bodies. Here we have Kirchhoff law, which is stating for all bodies at a thermal equilibrium, the emissivity and absorptivity are equal. So here you can consider a radiating enclosure. Within this, first I will be placing a sample body or real body which is having the properties of emissivity epsilon and absorptivity alpha, and it is having a total surface area of A. And since this enclosure, that is surrounding enclosure within which this real body is placed, is capable of radiating, means it can emit energy. So this will be radiating energy, and this radiating energy will be falling on the surface of real body. So this will be acting as an incident energy for this real body, which I will be calling it as irradiation. So irradiation on this real body is named as G, as G is per unit area we are defining. So the total energy incident, if the real body is having a total area of A, then total energy incident will be G times A. And out of this, if it is having an absorptivity of alpha, the energy absorbed by the real body will be equal to absorptivity into G into A. And also every body above some absolute Kelvin temperature will be able to radiate or emit, and the energy emitted will be equal to the emissive power into area. Emissive power, we are defining energy emitted per unit area, so into area will be giving the total energy emitted. And at equilibrium, at a thermal equilibrium, the energy absorbed by this body will be equal to energy emitted. That means what much amount of energy is being absorbed, the same will be emitted by this body at equilibrium. So you can equate this E times A equal to alpha into G into A. This I will be calling as 1. And this were considered for a real body. Now we will be replacing this real body by a black body. So this sample real body will be replaced, and this black body will be kept in this space. Again, you can write the energy absorbed and energy emitted by the black body. So energy emitted by the black body can be written as EB, the emissive power of black into total area, equal to energy absorbed will be absorptivity of black body into G into A. This equation I will be calling as 2. Now I will be taking the ratio of equation 1 and 2. Then left hand side E divided by EB equal to G A G are common for both 1 and 2 on right hand side. So E by EB will be equal to alpha divided by alpha B. And you know that black body is a perfect absorber for which absorptivity value is 1. So alpha B you can substitute as 1. And on left hand side you are having the emissive power of a real body to emissive power of black body, which is actually the ratio which is known as emissivity. So you can write it as epsilon. So on left hand side you are having epsilon and on right hand side you are having the absorptivity. So you can find that for all bodies which are at the thermal equilibrium, the emissivity can be equated to absorptivity, which this relation we will be using for solving many problems. And as for non-equilibrium conditions also, this condition is approximately satisfying. So this is Kirchhoff law.